Hey everyone, Jonathan Bailor back, folks. I know that I always say I'm excited about these podcasts, but I am uniquely excited about this podcast because we have the good fortune of being joined by one of the researchers whose work and related works is just so seminal to not only my life, but everything we talk about with the homeostatic regulation of weight, the set point of fixing our biology rather than fighting against it. And that is none other than Stephan Guyenet over with the University of Washington, the proprietor of wholehealthsource.org. And Stephan will inform us of wonderful research he's done, but suffice to say, he's a brilliant man. He's got his PhD in neurobiology from our backyard here at the University of Washington, and has authored some of my favorite papers on the homeostatic regulation of weight, or the set point. And our goal is to make this show the place where, if you are interested in the technical ins and outs of what we mean by the body works to balance itself out as long as we don't break our brain, where you can get that definition. So, Stephan, welcome to the show.
Thanks, Jonathan.
Well, Stephan, I am so thrilled again to have you sharing your time with us. And as I mentioned prior to the show, I'm hoping in as meticulous and structured of a fashion as we can. I just want to geek out because while it is widely accepted that, for example, blood sugar is homeostatically regulated and blood pressure is homeostatically regulated, and it's just a given, for some reason there still seems to be this woo-woo vibe in some people's minds about the homeostatic regulation of weight. What is that? And let's just break down why that is false.
You mean, why is there resistance to that idea?
Exactly.
Well, I think the reason why there's resistance to that idea is because there are both homeostatic and non-homeostatic influences on body weight. I mean, you can take a person and deliberately overfeed them. You can take someone and say, okay, we're going to feed you 1,000 extra calories a day, and that person will gain fat due to that deliberate overfeeding. So, I mean, there can be influences that are not homeostatically regulated that can influence body fatness. But that doesn't take away from the fact that we have this sophisticated system in the brain that regulates a variety of factors pertaining to body fatness.
And Stephan, just real quick, I love what you said there. And I often think to myself, though, I mean, again, people don't question the homeostatic regulation of blood sugar, yet we have diabetics. And they don't question the homeostatic regulation of blood pressure, yet you can have hypertension. And what confuses me a bit is just because we can overwhelm the homeostatic system clearly doesn't disprove its existence.
Yeah, that's right. And, there are a lot of studies that show that a variety of environmental conditions, things like plate size and, calorie density of the food and atmosphere of the eating environment, things like that can influence meal intake, calorie intake at a meal. And so people will say, well, if there's this homeostatic regulation going on, why are there all these things that have nothing to do with calories that influencing the balance of, energy in, energy out, and potentially influencing body fatness? And I think, not to diminish the importance of those observations, but that does not rule out the fact that there's also a sort of guiding force that nudges us in a homeostatic direction on a long-term basis.
And Stephan, correct me if I'm wrong, which I hope you would do anyway, because you really are the expert here. I'm just a mouthpiece for researchers such as yourself and Dr. Schwartz, for example. But in my simplistic mind, if you have studies which show that, for example, if I overfeed a person 1,000 calories a day, and they consistently, in dare I say, hundreds of studies, gain less than would be predicted by calorie math as is traditionally presented to us. And if you underfeed people in separate studies 1,000 calories and they gain less than would be predicted by calorie math, doesn't that in and of itself show that the body is not some passive vehicle that just adheres to calorie math, but plays a role in this?
Yeah, I mean, frankly, the Yeah, I mean, the body is obviously defending body fatness to a certain degree. I mean, my view on this, frankly, is that people who don't think that there's any sort of defense of body fatness are simply not aware of the research, because we have research going back to the mid 1800s demonstrating that centers in the brain regulate body fatness. Mm-hmm. And there's an entire sophisticated network of brain regions whose main function, or at least one of the most important function of those brain networks, is homeostatically regulating body fatness. And so if there was no homeostatic regulation of body fatness, why do we have this sophisticated network of brain regions that we've already identified in rodents and in humans that do exactly what they're not supposed to do? So I think, frankly, it's people that aren't quite connecting on a research level. Maybe someone who studies influences on food intake that aren't related to homeostasis might not think that homeostasis is an important variable in the equation.
I think that's a great point, Stephan. And I mean, if we look at, for example, your formal training, it is in neurobiology, which traditionally, if someone were to think about nutrition or diet or weight loss, they wouldn't necessarily be like, yes, I should ask the neurobiologist what I should do. But in fact, that is obviously a hugely important field when we talk about this area. So might that have something to do with it? People just aren't opening their neurobiology textbooks when they think about this?
Yeah, I think so. I mean, neurobiology is a field unto itself, and it's complicated, and most people don't have a background in it. And the fact is that energy homeostasis relates in large part to behaviors such as food intake, and behaviors such as how much you move your body, either actively or passively, consciously or unconsciously. There is, of course, an influence of the basal metabolic rate that's independent of those things, but compared to the behaviors of food intake and physical activity together, it's not as large of it can't be varied as much as physical activity and food intake, and therefore it's not as large a determinant. So, I mean, the point is that behaviors are generated by the brain. I don't think anyone would deny that. It's just common sense. And so the brain obviously plays an important role. And, the factors that determine the brain's selection of behavioral outcomes are the factors that in large part are going to determine body fatness, energy balance, and body fatness. So that's part of it. But I mean, to take a step back and take an even broader approach, the brain is basically the driver's seat for the body. It's the command center that regulates virtually every large-scale homeostatic process in the body. If you're talking about body temperature, the brain. If you're talking about blood pressure, the brain. If you're talking about what else? Well,
blood pressure,
blanking here, but there are a variety of other things that are homeostatic variables that are regulated by the brain. Blood glucose, for example. So that doesn't mean the brain is the only thing that's regulating those processes, but the brain plays a high-level regulatory role to nudge those things back into the optimal range when they're exiting the optimal range. And so, it makes sense, since the brain is the command center of the body, that it also plays a role in regulating body fatness.
And it seems, Stephan, that it's such an important distinction, because if we leave the brain out of the equation, there are, which again, like you said, the brain is everything. I mean, that's your brain is you in a sense. And if we leave that out of the equation, there are factors. For example, if eating certain types of foods or engaging in certain types of behaviors, for lack of better terms, break our brain. Like, it may have nothing to do with caloric intake. I know you have some research, which I want to get into, about substances which may cause inflammation in the brain, which if you break your brain and you think the solution to that is just to starve yourself, I mean, that's not, again, you're sort of missing, like, if you do not acknowledge the existence of the brain in this process, and the problem is fundamentally rooted in the brain, then you really have no hope of ever solving the problem, right?
Well, I mean, you can lose weight by restricting calories. We know that regardless of what the calories are coming from, if you sufficiently restrict calories, you're going to lose body fat. So it's not that you can't do it without engaging the homeostatic pathways. It's just that if you do it without engaging the homeostatic pathways, without working with the homeostatic pathways, you're going to be doing it in a more difficult manner. It's going to be essentially your conscious mind, your conscious long-term goals, your conscious self fighting against your unconscious self, this homeostatic regulation that's making you feel hungry, that's making you feel lethargic, that's making you have increased thoughts and desire for food, particularly calorie-dense, highly palatable foods. I mean, these are all things that have been documented to occur with calorie restriction. It's part of the brain's program to try to regain lost body fat. If a lean person, such as you or myself, were to lose body fat, that's probably not a good thing. I mean, that's not a good thing for survival in a natural context, because you need a certain amount of fat tissue. Fat is an endocrine organ that's important for the overall functioning of the body. And critically, it's also a very important energy reserve. So the brain is going to react negatively to that, and it's going to do what it can, enact this broad program to try to restore that lost fat in a variety of different ways. That being said, and I'm sure we'll get into this more later, but basically the same thing happens in an obese person. Their brain doesn't really see them as obese. It sees them as the same as a lean person's brain does, as having the right amount of fat mass. So when they try to lose, their brain enacts that very same program and opposes the loss of fat. That's not to say they can't lose the fat by, eating a low calorie diet of pizza and donuts and, going to the gym for 2 hours a day. Not to say that that doesn't work. It does work if you stick to it in terms of reducing body fat, but it's not going to be very pleasant, and for the average person, it's not going to be very effective because you're essentially fighting yourself. And those unconscious drives that are engaged, those are designed to wear you down. You're not supposed to be able to override those. I mean, if you have an iron will, maybe you can for a while, but I mean, they are designed to essentially wear you down so that you don't hurt yourself. That's what they're there for. There's another point I want to make just really briefly before we move on, and that is that, you mentioned that if you break the homeostatic system, then you have to address the homeostatic system. And I'd prefer to think of it in different terms than breaking it. I see where you're coming from, but what I like to think about is more of a mismatch between not necessarily that it's broken, but that there's a mismatch between the environment and the environment that your brain is kind of hardwired to deal with. And when that occurs, you get maladaptive outcomes, basically.
I like that distinction, Stephan. And I also like what you said earlier about it's not that the traditional just work harder, eat less, exercise more doesn't cause you to lose weight, because obviously it does. The question is sustainability. And it reminds me, while you were talking, it just thought of the analogy of if you're on the first floor of Sears and you want to get to the second floor of Sears, you could walk up the down escalator and you could get to the second floor by trying to walk up the down escalator. It's just much harder. Why not just take the up escalator and walk? Why not work with the escalator rather than working against it? And is that somewhat of a fair analogy for what we're talking about here?
Yeah, I think that's absolutely true. It's not a matter of efficacy under calorie-controlled conditions, or it's not a major matter of efficacy under calorie-controlled conditions. It's a matter of efficacy under real-life conditions where we have people engaging in normal behaviors, people who are human, and people who want the most sustainable route. They don't want to be fighting themselves. They don't want to do something that has 80-90% chance of being unsustainable at the 1 year time point. They want something that feels natural, where they can just engage in natural eating behaviors, not obsess about food, not count calories, but engage in natural eating behaviors, feel good about it, and also maintain, the amount of body fatness that they would prefer.
Well, Stephan, let's dig into and geek out a bit. And again, I want to invite the listeners to embrace the geeking out that we will do, because I think it's actually very, very powerful. Because once the more Stephan, for me at least, the more I understood the actual homeostatic system, the more you dig into it, the more real it becomes, because you understand it. And for me, that's actually very freeing, because when there's like, oh yeah, Jonathan and Stephan say there's this set point, and that's neat. They seem like credible guys. That's one thing, but to really get it and understand why it works, I think can be very empowering. When you hear constantly from the media, just eat 100-calorie snack packs, this can help give you an alternate mindset. So if you don't mind, Stephan, can we just, I don't know how to best describe this because it is quite complicated, but can we step through a little bit what this homeostatic system is, the brain components, the adipose tissue components, all that kind of fun stuff?
Yeah, sure. So at the broadest level, the brain is basically an organ that in large part gathers information about your environment, where you are, what's going on outside of you using the senses. And then it also gathers a lot of information that's internal. It's kind of gauging your internal state. And then it integrates all of that information into other brain regions that basically decide on what action to take, either behaviors outside your body or actions inside your body, like metabolic changes, insulin secretion, release of fatty acids from fat tissue, glycogen synthesis, et cetera, heart rate. So that's basically the overarching idea of what the brain's doing. So, and it does all that to promote essentially survival and reproduction. That's the overarching goal of the organism. And so one of the aspects of that is maintaining adequate energy stores. So you need to have adequate energy stores if you want to survive periods of low food availability, or if you have big things you have to do, like have a baby, for example. You have to have a certain amount of fat to protect yourself from variability in your food supply and in your calorie expenditure. So the brain essentially measures, let me take another little step back. There's basically two systems that we can identify that are involved in energy homeostasis. So maintaining somewhat stable energy stores. There's one that operates on the short-term meal-to-meal basis, and that machinery is located primarily in the brainstem. And then there's one that operates on a longer-term scale and regulates body fatness, and that one's located primarily in the hypothalamus. So that, I'm simplifying because there are elements in other parts of the brain, but those are the primary areas for each of those. So, and I'll start off with the meal-to-meal homeostasis because it's the easiest to understand, and it's very intuitive, really. So there are negative consequences associated with eating too little, and there are also negative consequences associated with eating too much. For example, if you eat too little, you might not have enough energy to do what you want to do for the day. If you eat too much, you can stress the digestive system, you can stress the metabolism, you can stress your digestive organs, etc. It turns out that your stomach has a much larger capacity for food than almost anyone ever fills. I mean, you see a guy like, what was the swimming champion in the Olympics, Michael Phelps. What was he eating, like 12,000 calories a day?
Yes.
Can you imagine the size of that guy's meals? I mean, I'm sure he ate multiple meals, but that's more than 4 times the number of calories that most people eat. I mean, I'm an active person. I eat a fair amount of calories. That's more than 4 times the number of calories that I eat, which is insane to think about. But the point is that the stomach can hold a lot of food. It can hold a lot more food than we habitually put into it. So why does it feel like your stomach's about to explode when you eat an amount of food that's only filling up your stomach halfway? The reason is this short-term meal-to-meal energy homeostasis called the satiety system. So basically, when your body senses that you've had enough food to fulfill your metabolic needs based on your habitual meal pattern, then it sends signals to the brain via stretch receptors in the stomach and via a variety of gut hormones that communicate to the brain. A lot of it's going through the vagus nerve. Some of it's going through the circulation and directly impacting on the brainstem. And that says, basically, we just ate X number of calories, and the composition of those calories was roughly XYZ. So, and it's not a perfect system. It's not perfectly accurate about how it reports those things. And that's something we can use to our advantage to manipulate satiety per calorie. However, that is the basic function of the system. So that's the short-term thing. So basically, it's a negative feedback loop that's limiting meal size, so that you aren't going to overeat. So basically, you're hungry as the default state, and then as you continue to eat, the satiety system kicks in and limits meal size. So you have basically limits. The hunger is setting your lower limit, and then the satiety is setting your upper limit of food intake. So that's the short-term homeostatic regulation system. The long-term homeostatic system is, so again, in the same way that the brain is measuring the internal state of the body by monitoring the digestive tract after you eat a meal, the brain, and this time is primarily the hypothalamus, is monitoring the size of your body fat stores. So like any negative feedback system, just like the thermostat in your house, you have to have a signal that's traveling from body fat to get to your sensor. And so that signal in this case is primarily the hormone leptin. So leptin is a peptide hormone that's produced in proportion to body fatness, travels through the circulation and gets to the brain where I forgot to mention, leptin is secreted into the circulation in proportion to fat tissue size. So that's how the brain measures body fatness. The more leptin there is, the more the brain thinks, the more fat it thinks you have. Leptin is also responsive to the amount of food that you've eaten over a 2 or 3 day period. So if you ate a lot for a couple of days, you would also have disproportionately high leptin for your level of body fatness. And leptin kind of sets the tone on, among other things, it kind of sets the tone on the satiety system. So if you haven't eaten as much as you usually eat for a few days, your leptin is going to be lower. Your body fat's going to have dropped a little bit. Your leptin's also going to be lower because you haven't eaten much over the last few days. And that basically decreases the responsiveness of your brainstem to those satiety signals. So it takes more food to allow you to achieve satiety because your body is basically enacting a program to regain that energy deficit. So, so leptin acts in the brain in a variety of ways to manipulate or to influence, to regulate body fatness. So it influences energy expenditure, including the basal metabolic rate. And that's just the amount of energy that your body burns just doing housekeeping, regular, whatever, DNA synthesis, protein synthesis, keeping your neurons polarized, etc. That all takes a lot of energy. And a large decrease in leptin can modestly decrease the amount of energy that's being used for that. But the more important thing, and it does that in part through affecting thyroid signaling. Basically, the hypothalamus controls thyroid, indirectly controls the thyroid hormone. So if it detects an energy deficit, it can shut down your metabolic rate to some degree through reduction of thyroid hormone. And conversely, if you're eating more, it works in the opposite direction too. If you're eating more, your brain can increase your metabolic rate to a limited degree. So in rodents, that effect is really well documented. It's very consistent. In humans, it's a little more squirrely. The effects on basal metabolic rate specifically are a little bit more squirrely. And part of the reason is humans really don't have nearly as much brown fat as rodents. So that's a type of fat that burns fatty acids to produce energy. And rodents have a ton of it. They're small mammals. They are very threatened by the possibility of hypothermia. So they have a lot of brown fat. Humans have a little bit between the shoulder blades and around the neck area. But anyway, the main point I want to make is that the brain can homeostatically regulate energy expenditure, but it's mostly via the efficiency of muscular contraction and via something called non-exercise activity thermogenesis. So that's basically involuntary fidgeting. People, tap their feet, move their hands, change their posture, etc. That studies have shown is capable of dissipating several hundred calories a day during deliberate overfeeding. So it's a major mechanism of calorie dissipation that's under presumably it's under unconscious control, presumably under the control of that energy homeostasis system. And conversely, so leptin controls the amount of energy going out of your body. So if you're not eating as much, it can reduce energy out. If you're eating more, it can increase energy out. But it also has a major impact on the amount of energy that's going into the body by controlling hunger. And so there's this really interesting phenomenon in humans whereby if you overeat today, you probably won't undereat the next day, but studies have shown that you probably will undereat 2 days from now or 3 days from now. So there's this kind of long-term delayed compensation that occurs. And I think that's actually, interestingly, one of the main things that prevents people from seeing these homeostatic effects, as they're so long-term. And many of the studies that are looking at food intake are very short. So it's really hard to pick up on these things that might have a major impact in the long term. So anyway, that's basically an overview. Oh, and I want to mention too, before we get off this topic, that it's not just leptin. There are a variety of signals that are impacting on the brain. And leptin is the major one that represents body fatness, but there are a variety of signals that participate in this homeostatic regulation process. So that's a summary of how those systems work.
Stephan, thank you so much. I think that's so, it's wonderful to get that level of depth and understanding, because again, I think it really grounds us and helps us. The more we can see this beautiful complexity that is our body and our body weight and our really our physiology, the more statements like just eat less, or you're just lazy, or you're just a glutton start to be like, all right, if someone's unhappy, you don't just say smile more, be happy. Like human psychology is complicated. We need to kind of dig below the surface, dig below the sound bites, and understand what's going on. You can't just say, well, smile more and frown less and you'll be happier. It's the same kind of thing with when we understand that our biology is as complicated as our psychology. We start to appreciate that a little bit more. And Stephan, the question though then becomes, what are the ways you've seen, and I know this is an area where it's not like there is conclusive evidence that X, so we have to do the best we can with what we have, but what do you see as the most promising approaches to re-regulating, maybe for lack of better terms, this homeostatic system such that it does not think we're slim when we're actually not slim, and works to defend a slim weight like many of us currently are defending a non-slim weight?
Yeah. So my take is that if we're going to do that, if we're going to make an attempt at sustainably reducing body fatness, then it should be an attempt that tries to address both homeostatic and non-homeostatic influences on food intake and energy expenditure. Because, it is true that there are non-homeostatic influences on food intake, and I think those are meaningful. Like just having food available, having tempting food available all the time is going to tend to make people want to eat more. So I really focus a lot on trying to get people to improve their food environment, create an environment that consistently favors positive choices and makes negative choices more difficult. And you can't eat something that's not there, and you're probably not even going to be tempted by something that's not there if there's no cue around that reminds you of that thing. So that's one part of it. But if we're gonna address the homeostatic system, there are a variety of things that are known or suspected to influence the homeostatic regulation of body fatness that we can use to leverage this system that we've been talking about. So I think one of the more important ones is protein. There's been a lot of research on protein over the last couple of decades, and it's only accelerating. And protein works on a couple of different levels. It works on the satiety system because protein is the most satiating macronutrient among protein, carbohydrate, and fat, and per unit calorie, that is. And but also elements of protein, particularly the leucine, have been shown to act directly on energy balance centers in the hypothalamus. So leucine particularly impacts a pathway called the mTOR pathway. It's one of the major intracellular energy sensing pathways of the body. So sort of like leptin is a whole body energy sensor, mTOR and another protein, AMP kinase, are the major cellular energy sensors. And mTOR is particularly responsive to amino acids, and particularly the amino acid leucine. And so when you eat a high protein diet, you're increasing signaling through this pathway, and potentially that plays a role in homeostatically re-regulating to a lower level. And you see this a lot. You see people who...
Well, hey, Stephan,
increase their protein intake, and suddenly they're spontaneously eating fewer calories. Yep. Can you hear me?
Oh, sorry. Yeah.
Hello?
Got you back. You're there.
Okay. All right.
Spontaneous caloric reduction is where you were saying.
Yeah. Okay. So when you do a study and you put people on a certain diet regimen, and suddenly they're eating several hundred calories fewer, even though they weren't being asked to restrict calories, and they're losing a significant amount of body fat, without trying, without feeling hungry, etc., then I think that's pretty compelling evidence. At least it's suggestive, it's strongly suggestive that you're having effects on the energy homeostasis system to reduce the defended level of body fatness. And protein certainly qualifies for that in human studies. And it's been shown, as I said, that it directly acts in the hypothalamus in rodent studies. So we have, and it's also been shown that when someone loses weight on a high protein diet, you don't see the expected disproportionate reduction in metabolic rate that would occur with calorie restriction normally on a non-high protein diet. So basically all signs point to protein actually acting directly on those energy homeostasis circuits and re-regulating them to a lower level in conditions of overweight and obesity.
Stephan, can I say a quick question just to get your expert opinion here? So, I love me some protein. So I'm a big fan of that. And I've just kind of wondered, this is more totally theoretical, but I sometimes wonder if, like, why does that happen? Obviously we talk about mTOR, but I'm saying more meta evolutionary level. And do you think, and this is obviously it's just a hypothesis, but it seems like maybe an abundance of protein seems to signal a abundant food environment. Like protein is a major structural component and historically relatively scarce a substance for us to get. So when our body is presented with an abundance of, let's call it the gold standard of structural components it needs to stay alive, 200 calories of protein are going to be perceived, for lack of better terms, much differently than 200 calories of carbohydrate. It's a valuable commodity, for lack of better terms, in the body's mind. Did that make any sense or seem reasonable at all?
Well, yeah, I understand what you're saying. I mean, I've given this some thought as well. I mean, the fact is you can come up with a variety of teleological arguments about why protein is satiating, but personally, I don't feel sufficiently compelled by any of them to speculate. But what I will say, so there's this idea, the protein leverage hypothesis. Have you heard of this?
Oh, no, the listeners would love to hear. Go ahead.
Okay, so protein leverage hypothesis is basically the idea that that our bodies want to obtain a certain absolute quantity of protein. And so if you're eating a diet that's more concentrated in protein, you have to eat fewer calories to obtain that. And so you'll eat less. And then also this hypothesis would predict also that if you eat a low protein diet, you would eat more to be able to maintain a consistent protein intake. The problem is that doesn't happen. When you reduce protein intake, calorie intake does not go up. It remains approximately the same when you go from normal to low protein. So I think this is really an effect that's specific to elevated protein intakes. And I really don't know, teleologically what evolutionary function it would have had. I've thought about this, and I have to say that I'm rather stumped about it.
No, that's fair. And most importantly, we've got the research that points to it seems to work. So why, at least, give me the placebo. Like, if it's going to make me feel better, this isn't a placebo in this case. But if the results are there, I'll take it, even if we can't necessarily explain why. So that's all good for me.
Yeah, I mean, and the results are there. Protein, I would say, is one of the more compelling approaches that have been identified to date.
All right, so we've got protein. You also mentioned, of course, just general satiety signals in the digestive organs, which obviously food size plays a role there. So water and fiber must also play a role in this system. If that's incorrect, please correct me if I'm wrong. But assuming they are correct, what else? What else can we do to potentially manipulate the system?
Yeah, I mean, certainly what you said, water and fiber, those are major factors in satiety per unit calorie of food. So the more, to a point, You can't eat 0 calorie, high fiber, high water foods and feel satisfied. To a point, things that are higher in water and higher in fiber are going to be more filling per unit calorie. And that's something that probably acts primarily on the short-term energy homeostasis pathways, the satiety system, not necessarily going to have much impact on the homeostatic regulation of body fat in the longer term. But I mean, let me rephrase that. I think it can impact body fatness to some degree, but it's not necessarily going to impact the homeostatic regulation of body fat in a way that's going to make you really lose large amounts of weight. That's my opinion. But that being said, there's another thing that's related to fiber, and that's the health of the digestive flora. And I'm not going to take this one too far. I've done quite a bit of reading on this, and my AHS 2012 talk was on this topic. And there's a lot of hype about the gut flora, so I'm not going to take it too far because I don't think the evidence is there yet to be making grand claims. But that being said, I mean, I think there is enough evidence to strongly suspect that the gut flora do have an impact on body fatness. And that may be through homeostatic influences. It's hard to say for sure at this point. But we do know that, for example, certain types of antibiotic use can be associated with weight gain. We know that C-sections are associated with childhood obesity in the offspring. Not clear whether those are causal relationships, but the association has been noted. And then in animal models, it's very clear, in rodent models, it's very clear that the gut flora can have a strong impact on body fatness. So for example, you can take an animal, you can feed it a fattening diet, animal will get fat. You can take its gut flora and transfer it to a sterile mouse, so an animal that doesn't have any gut flora, and it will actually make that animal fat that received that gut flora. Whereas if you take gut flora from a lean animal and give it to a sterile animal, it will not make that animal fat. So there is a certain amount of information that seems to be carried in the composition of the gut flora as well. And the point of me bringing this up now is to bring it back around to the fiber content of the diet, because gut flora are very strongly influenced by the fermentable fiber content of the diet. So if you're eating a diet that is rich in a variety of fermentable fibers, then you're more likely to have a large and diverse and thriving community of gut flora that are helping you maintain a healthy weight rather than hindering it.
I love it, Stephan. I love it. Well, what do you think is next? Do you see anything on the horizon for where the research is headed in the homeostatic weight regulation arena? What are the key questions that are trying to be answered right now?
Well, one of the really big questions is what exactly is the mechanism that causes the defended level of body fatness to increase? So, I mean, we know how to do it empirically. We can put animals on a fattening diet, certain types of fattening diets, and we can make them obese readily, and that's associated with the defense of the increased body fatness. You can make an animal obese on these diets, and I can tell you what's in the diet. It's composed entirely of refined ingredients. It's 60% calories from fat, 20% from protein, and 20% from refined carbohydrate, with some vitamins and minerals and a little bit of fiber added in. And rodents will become markedly obese within just 1 or 2 months on this stuff. In fact, in my own hands, rats will double in body fatness in as little as 2 weeks. Their body fatness will double. They eat it voraciously, at least at first, and they very efficiently pack on fat tissue. So we know that that happens. We don't know exactly what it is about these diets that causes that to happen. We don't know whether it's the fat content. We don't know whether it's the lack of fermentable fibers, fatty acid composition, the type of protein. I say we don't know. Actually, there are quite a number of clues. And one of them, frankly, is just that the animals really, really like the food. It's highly palatable, highly rewarding. When you first expose them to it, they literally eat double the number of calories that they would normally eat for approximately the first week. And then they kind of start to level off in calorie intake. But it's basically like cookie dough. You can look at it, you can play with it. I mean, it's not very appealing to me or you. It's not something you want to sit there and eat a plate full of. But to a rat that spent its entire life eating this high fiber, whole foods, hard pellet that's about 14% fat and about 70% carbohydrate, that tastes awesome. When that's all a rat's ever eaten for its entire life is this one food. I mean, this is like the potato diet, Chris Voigt. It's you eat one food for your entire life, and then you get another food that tastes better, and you're going to like it, and you're going to eat more. So, and this touches on something else too that I'll just take a brief tangent here. But so when you give them this food, it's novel. They really like the taste, so they eat a bunch. Eventually, after 7 to 10 days, their calorie intake actually drops back down to normal, even though they continue to gain weight. And but interestingly, there are ways to keep getting them to eat calories so that they won't level off. And basically, the way you do that is you present them with a variety of highly palatable foods. You present them with a variety of junk foods. It's called the cafeteria diet. It's somewhat commonly used fattening diet in our field. It's extremely fattening. You just put a variety of junk food in their cage, and just giving them that choice, that variety, keeps their food intake high. And so they'll continue to gorge themselves, and they'll continue to keep their calorie intake high, and they'll gain fat at a more rapid rate than an animal that's just eating this high fat pellet that we give them. So that being said, anyway, that's a tangent. But the point I want to circle back around to is we don't really know exactly what it is about this food that is causing them to be obese. And what I would really like to have is a complete map of the mechanism from the food, not even going into their mouth, from them seeing the food, from them smelling the food, then entering the mouth, being digested, metabolic signals going to the brain, nutrients, fatty acids, amino acids, etc., going into the brain, food going through the digestive tract and getting metabolized by gut bacteria, bacterial components potentially translocating into the blood, all of that. How is that resulting in not just the animals eating more and gaining fat, but actually becoming fat and resisting fat loss when you try to put them on a diet?
Mm-hmm.
So this is the same thing we see in humans. It's very easy to replicate in animals. If you give them this diet, this fattening diet, they will gain a remarkable amount of fat, and then you can restrict them. You can restrict their calories, but not switch them off the diet. You give them the same diet, you restrict their calories, and their bodies will fight it. They'll fight it hard. So they'll reduce their energy expenditure. They will increase their food-seeking activity, and if you give them access to as much food as they want after dieting them, they'll immediately regain back to the same place that they would have been if you never had dieted them. So it's exactly the same thing. Obviously, humans are a lot more complex, and we have a lot of things going on, like goals and social stuff and all that. So it's not a perfect analogy, but I mean, the basic fact of homeostatic regulation is there. But interestingly, and this is something that's been shown previously and also in my own hands, is that the defended level of body fatness is very specific to the specific conditions that the animals are under at the time. So if you take that diet, that very fattening diet, and you give them half as much, they'll lose weight and they'll initiate this, this program to try to regain the weight. But if instead of doing that, you just switch them back onto their regular chow, this is the thing that they were on prior to the fattening diet. It's a whole food based diet that works pretty well with rodent physiology. And they will spontaneously eat less and they will spontaneously lose that fat, even if they have access to a ton of food. So it's very much dependent on the context. And the same thing if you give them a running wheel. If you give them a running wheel or you give them an enriched environment where they can socialize with other animals and they have toys, etc., they will be more resistant to gaining fat than if they don't have those things. Even if you let them have as much food as they want.
That's fascinating. I love animal models in some ways because you can eliminate all the when you get humans involved, it gets sticky quickly. But when you just use rats, you can do this cool stuff where you're like, oh, there's no emotional eating going on there, and it's so cool because you can see what you're doing. I mean, you're trying to emulate these human-like environments. I think that's really neat. That always makes me happy. Well, Stephan, I could frankly listen to this all day. This is what I live for. And I just wanted to thank you for the research you've done in this arena and hopefully continue to do, because I do think, hopefully it doesn't take this long, but in a few decades, we're going to look back on weight, just like we look back on blood sugar now. And, this is what the body is designed here to do. That doesn't mean we can't dysregulate the system, but it means there's a system, and if we want to walk up the down escalator, we can. But why not just walk down the down escalator? And Stephan, if I understand correctly, you do actually have a program which, for lack of better terms, may help people to walk down the down escalator rather than up the down escalator. Can you just tell us briefly a little bit about that?
Yeah, sure. So it's called the Ideal Weight Program, and it's a body fat loss program that I designed along with Dan Party with some support from a few other people. And basically it is a comprehensive diet and lifestyle program that's designed to work with the body to promote fat loss in a sustainable way. And so but the thing that's really unique about it, there are a couple of things that are really unique about it that I'll just say really briefly. One of them is that it really comes from a position of knowledge on homeostatic regulation of body fat and focuses on not counting calories, but living your life in a way that naturally promotes a reduced level of body fatness, which many people find that strategy works well for them. But the other thing that's really unique about it is it incorporates some very simple and effective tracking software, so you can track your physical activity and your sleep and your body weight and get objective feedback on those things so that you can meet the goals that you set through the program. And so we feel that sort of objective feedback that's made as easy as possible is really very critical for evaluating your progress and meeting your goals and motivating you as well.
Well, Stephan, certainly for all my listeners here, if you don't realize it, you have been influenced by Stephan's work even before you listen to this podcast, because, like I said, his work and his Michael Schwartz, is it fair to say he's your mentor, or do you just work with him, or how closely do you work with him?
Yeah, he's my mentor. I'm a postdoc in Mike Schwartz's lab, so it's fair to say that he's my mentor.
So yeah, and folks, if you're interested in this kind of stuff, like, please look up Stephan's work, not only on the in quotations regular internet at wholehealthsource.org. I'm going to define that as the regular internet, and then the non-regular internet, let's call that PubMed. If you really want to get at it, search for Stephan's work and then also his mentor, Michael Schwartz, or just look up their names and then University of Washington and check out their work over there. Obviously, I got that Washington pride because you're over here in the backyard. It's kind of nice that we've got one of the premier obesity research centers in the world right here in Washington. You wouldn't think that, but it's pretty awesome.
That's right.
So watch out, Washington. First, we brought out Macklemore. Then we brought out Stephan Guyenet. So you're going to be the next big star out of Washington, right?
All right. I'm going to need to get a new haircut.
I love it. Well, Stephan, thank you so much for joining us. And folks, again, if you want to learn more, Stephan's got just truly an amazing amount of information on his blog. I have no idea what his word count is, but there's lots. So please check out wholehealthsource.org. And again, the name of Stephan's homeostatic regulation of weight friendly weight program is called the Ideal Weight Program. You can find more information to that on his website. And again, Stephan, thank you so much for joining us. It's absolutely a pleasure.
Thanks, Jonathan.
Listeners, I hope you enjoyed today's show as much as I did. And remember, this week and every week after, eat smarter, exercise smarter, and live better. Talk with you soon.